Uh, hey y'all, this is Raj from Apple. I work as an engineering manager for Data Lakehouse team within AML data platform. Our group provides storage and streaming application services for machine learning, data engineering, and analytical use cases. Today we are going to talk about Apache Iceberg table optimization service we have built it in-house. There are two parts to this talk. First, I'll cover the introduction to Iceberg, which you guys are already know about that. But I'll try to cover some of the benefits what we have seen that matters to us, and what is that you need to run Iceberg at scale. My colleague Steve will talk about its core optimization service, which will call it as a smart Iceberg table optimizer, and he'll explain why it is smart and architecture and internals of it. Steve, would you like to intro?
Hey everyone, this is Hongyue and I go by Steve. Today I'm really happy to share my learning about Apache Iceberg, and then I'll pass back to Raj.
Thank you, Steve. So I've already covered mine, so I'm gonna jump into the talk. So what is Iceberg? We have seen Parquet, ORC as file formats, but what is table format? Table format is nothing but how do you lay out the files in a table. Let's talk more about comparing it with Apache Hive. Apache Hive is a distributed open source data warehouse over HDFS. It organizes the files as directories like DB name, table name, /partitions. All files in the directory are actual data files contribute to that partition. Depends on your predicate condition, it can actually look at the files in that partition or all the files in the table. Iceberg manages these files in a little bit different way. It follows a tree-like structure for metadata files. The metadata layer in the middle of the right side image has these metadata file, manifest list. Let's not jump into what each of these actually contains. Assume that these are the files, maintains the actual metadata and references to the data files that are based out of the snapshot. Let's talk more about the snapshot. Every commit operation in Iceberg creates a new snapshot. Snapshots refers to actual data files via these metadata files. Interesting point is not all files in the directory for an Iceberg table are contributing to the table or a partition. It's all dealt by the snapshot. We'll discuss a few benefits why we considered Iceberg in the first place while we were building this large-scale data platform. Iceberg is asset compliant, which we already know, and it allows concurrent IO operations. And this is not very common in traditional data lakes that you have seen. Users can perform update and delete operations, and this is very critical for us to consider why Iceberg matters to us. And this has become very critical for our infrastructure needs, especially where we have privacy and GDPR type of compliance. And in case of Hive, to delete or update, the general practice is we have to insert, override everything. Even though one file or one record is impacted, we have to read and write the petabytes of data, terabytes of data, whatever the table size is. And that's not efficient. It's a costly operation if you're doing it at even in the cloud environments. So time travel is another cool feature. We have seen growing the use cases in ML side. A lot of our ML users are actually trying to adopt Iceberg because of the time travel feature. We've built in-house tools to provide these kind of time travel features, and before we chose this Iceberg. The main reason is ML engineers would like to test the models with the previous version of the data. If the model is changed, they would like to test the scores. What was the previous score versus the new score after the model is changed? So that is very critical for us to validate the accuracy of the model. And snapshot here helps us to do the time travel and rollback. Hidden partition, this is something we have seen, people, we don't have to stick to one partition. Partitions can evolve over time. With hidden partitioning, Iceberg avoids reading unnecessary partitions automatically, and consumers don't need to know how the table is actually partitioned and add extra filters to their queries. And these are some of the things that we need to know if you're dealing with traditional Hive. We have noticed better performance and reliable writing using Iceberg to S3. the S3 writer inside open source Iceberg, we have seen some of the jobs run for a couple of hours without Iceberg, and they fail, like 6 hours of compute is waste. And we have to delete whatever the data that has been done and then rerun the job. So we have noticed that the reliability is a concern. If you're using Apache Iceberg libraries inside the Spark, the reliability is 100%. We have not seen a single job failed because of this particular reason. Let's talk about the last point, which are column level stats, which are very critical if you want to really optimize or use Iceberg at its full benefits. Sort order, Z order, min-max files. These min-max stats helps you to read less data, because if you want to increase the performance, read as less as possible. And we all know partitioning, which falls under this category, but with Iceberg, you can achieve more with this column level stats. Data retention in previous, so data retention, there are two versions to the data retention. One is soft delete. If you perform a delete on Iceberg table, it is actually a soft delete. It does not delete from the file system. Hard delete is what actually we treat it as disk of the files. And it is very important for various reasons. One is cost. You can decrease the cost of S3. And the other reason is functional reasons, privacy and GDPR. They want the files to be disk off. Even though they are not accessible to the read operations, they want the files to be disk off, so which is very critical. And Steve will talk about how to achieve these hard deletes without users worrying about how to deal with the data that was in the previous snapshots. Query performance, apart from column level stats that I explained in the previous slide, data and metadata compaction will increase the query performance by avoiding too many scan files. We have noticed if you're trying to list the partitions without the manifest rewrite operation, we have noticed for hourly commit tables, like it takes 15-20 minutes. That's a con side. If you take Hive maintains all the partitions in its metadata, so you get the partitions immediately. Whereas in Iceberg, it still needs to go to the manifest files and retrieve all the partitions. So what we have done is, with the manifest rewrite operation, the metadata will be optimized. So we have less than a minute, we have seen returning the list of partitions of the table. I'm talking about the large tables here. If you're running Iceberg at a production scale, thousands of tables, millions of files, and petabytes of data, some of these metrics helps, number of snapshots. It's not optimal to keep a table for the longer snapshots. So it's a good practice to expire them. Data and metadata file sizes, it is very important so that if you want to trigger something like data compaction or metadata compaction, these metrics will help us or provides inputs to the underlying system to run the jobs. Earliest and latest snapshot to see if a table is live or not. I'll hand over to Steve to talk about the second part of this talk.
Thank you, Raj. So we're trying to solve the problems above with our Smart Table Optimizer. It's our in-house solution to manage the Apache Iceberg at scale. In the next few slides, I'll talk about more in details. So at very high level, we can think of three components. It has the control planes, persistent layer, and the data planes. Control plane is the way we identify the optimization candidates, and we write its optimization parameters into the persistent layer. And the persistent layer, what we had is a collection of Iceberg tables. And the data plane is actually the one who applied the desired optimizations using the Apache Spark in distributed manners. At the end of execution, we also write the optimized results back to our persistent layer. So the diagram below showed how control plane and data plane work together. So we can see that because in control plane, we need to integrate with different plugins to source the list of the optimization candidates. And we need to apply the reasonable defaults. So we build the conflict resolution logic and deduplication into our spec processor. We'll process the table in order, apply the defaults, and then write this record in a batch to our own internal set of Iceberg tables in the persistent layer. So we decided to use Iceberg tables for our own internal data storage. This helps simplify our dependency graph. And we have a relatively simple read and write patterns in our jobs in the control plane and the data planes. So data plane, as you can see on the right-hand side, it's actually much larger. We group jobs by its functionalities. And some of the data plane jobs are just a parallelizable wrapper on top of Iceberg Spark actions. So we can see expire snapshots, remove orphans, compacting the small data files, and rerun manifests. Those are the required and optional maintenance tasks suggested by the Iceberg community. Other jobs, such as monitoring, this provides us the visibility into the business adoptions, into the cost reportings, and to make sure Icebergs are stay performant over time. So one of the questions we ask ourselves is, as we have more and more tables, are all of the tables we found in the Iceberg catalog worth the optimizing with? So optimizing help with query and provide user with consistent and robust experience, but at the cost of limited compute resource. So answer to this question is kind of dependent on business needs, but what we figured worked best for us in the past is judged based on the historical usage. So we built the integration with the Spark listeners, with the Trino execution events to figure out what's the hot partition being used, and this can benefit the most from our optimizations. But we also know that the past doesn't represent the futures. So we implement a mechanism to provide explicit opt-in and opt-out mechanism so that we can cover the table we know for certain. Another problem we have in the past is how do we track our execution histories? We started small. We can just search off our Spark application log to figure out the history executions. But as we are getting more and more tables under the management, we decide to persist all of this optimization inputs and output into a table format so that we can query these results later. Below, you can see the example for the orphan removals. We can see the Spark actions on the right-hand side, which probably needs a table identifier and older than timestamp to execute. And on the left-hand side, we model this input and output into the corresponding tables so that we can write this number of the orphan files removed, Spark application IDs into our own tables. Using Iceberg to store our own internal data sets, we can easily debug if there's a particular job failures, or we can see the aggregate trends of our optimization over time. And the best part is we can learn from our histories to decide what kind of optimization we should prioritize in the future. So speak of executions, let's dive deep into the remove orphans. So essentially, how Iceberg remove its orphan is comparing the desire with reality. So desire in this case are the number of files tracked by Iceberg metadata. And the reality here is number of the files we found on the underlying file systems. And if there's a divergence between the desired and the reality, then here comes the orphan files. Together with condition how old is these files, we can see if the given orphan can be safely removed or not. So important to know that this operation actually needs to scan all of the files tracked by Iceberg and also the files on the file system. So this can be the most time-consuming part of our data plane jobs. And this becomes more relevant if our underlying data storage is on the S3. Because for the S3, we know there's a known limitation. It can only list in up to 1,000 objects under a given prefix in a request. So as we see on this diagram, we see there's 8 files tracked by the Iceberg metadata, but we found actually 9 files on the file systems. This particular d3.parquet file, it's the orphan, and I think it should be removed. Given that, we know if we have more data being tracked in the Iceberg tables, it takes longer for entire operation to complete. We can try to improve by either reducing number of files tracked by Iceberg tables or remove the number of files found on the file system under the given prefix. So this leads us to the next slides on the data compactions. So Apache Iceberg offers a way to stream the data into the table with a high parallelism. But oftentimes, this implies that we are also running into the small files problems. By compacting those small files together with sorting, we'll improve our read performance. Reducing number of files means we're spend less time on open and close files when we're trying to do the read. Currently, the data compaction allows us to optimize on partition levels instead of compact all of the data files we found in a table. However, the data compaction will only create the larger files in a new snapshot. It does not really clean up the previously small data files. In order to handle this destructive part, we actually need to look at another Iceberg operation called the expire snapshots. So snapshot, as Manny mentioned, it's an Iceberg primitive to track all of the data change. It enables the beloved time travel features, where data consumer can actually go back in time and look at data at a particular timestamp. However, this implies we're getting more and more complexity when we're trying to remove a file. So a file can be safely removed from Iceberg if there's no metadata reference to that. And this came to rescue with the expire snapshot actions so that they can identify the snapshot to expire first and then remove all of the files which only is reachable by these expired snapshots. So let's look at an example. Using the data compaction example we had in the previous slides, we can see that manifest M2, data file D2 and D3 can be safely deleted because snapshot S1 is removed, it's expiring. Because only these metadata and data files are reachable by the expired snapshots. Looking at the size distribution of all the table under the management, we realize a few interesting things. Those tables are like marine animals. We find out there's many small tables like anchovies. They are not get updated often, maybe get read once or twice per week. But there's also the problem of whale tables with extremely high throughput and resource hungry for the optimizations. So it's important to group them by different silos. We can allocate corresponding CPU and memory resource so that we can schedule them as different cadence to meet our optimization promise and avoid resource contention between them. Since the data plane operation is most heavy work, we start by separating table under management into logical groups we call silos. There are no overlapping tables across the silos, and we can scale our data plane operation simply by adding more silos. And there are always the need to actually separate data by the physical separations. So we build another mechanism to build control plane in new account to scale our entire system for the both control plane and data plane. I think that's what I have. I would like to pass back to Raj.
Thank you, Steve. So this is the last slide of this talk. So in this slide, we'll talk about some of the contributions we have done back to the upstream. We use open source Iceberg. We are on 1.0. But we have branched out for internal use, and we have some of the patches, customizations that to work with our other ecosystems. We are continuously providing some commits with features and bug fixes and specs to the upstream. In last quarter itself, like we have done like 20 plus commits. I've listed some of those here. We can actually. We are also looking at implementing IRC, Iceberg REST catalog. So yeah, that's another one. So we don't have, the spec is released, but we don't have the implementation. Today we are we relied on as a catalog. The catalog options are either Hive Metastore or we have Glue catalog, Project Nessie, and yeah, some of the other enterprise catalogs, but we don't have a proper catalog which actually supports for Spark consumers as well as for the non-Spark consumers. Like, it supports Spark and Trino, but what if a distributed processing engine is something else, right? So we are looking in the direction. So yeah, that's about the talk.
There we go. Thanks, Steve. Thanks, Raj. Any questions here in the room? There.
Hi, do you all do any data quality analysis on your metadata? And if so, what kind of metrics do you collect?
Do you want me to take? Okay, so I guess the question is, do we do any data quality check on the metadatas? I think this is actually one of the highly requested features from our customers. So our downstream users were actually data engineers, data analytics. They care about the actual data qualities. So for us, our team is mostly the data infrastructures. So we're providing the ways and the tools for them to, because we don't know the specific data sets, there are too many data sets, we can't have the generic quality check on all of them. So we provide them tools and runbook so that they can actually run the Iceberg metadata queries to check if the data ingested right into the tables are being tested against their own scenarios. Because every team has a different quality standards, whether or not there's enough records or there's a specific new value counts in the tables. We provide them ways how this can be done in the Iceberg tables, but we don't do them like at scale for all of our customers. I hope that answered your question.
Great, thanks. Any other questions here in the room? Cool, we do have a couple here online. If anyone else comes up with a question, let me know, raise your hand. One of the questions was, you said you used the Spark listener in the Trino event, the listeners. Is there a reason why you chose that over the existing Iceberg listener framework?
So I think because all of our downstream users actually query the Iceberg tables using Spark and Trinos. So we started there because this is a mechanism for our user to actually query the Iceberg tables. I figure it's more representative of how data are being used in our organization. So we start here. But I think we're also going to look into the Iceberg listeners if there's any.
Cool, that makes sense, thanks. There was another question here. Will any of the work that you guys have done around the automatic optimization, so not necessarily Spark actions, the stuff that's already in, rewrite data files, that kind of stuff that's already in the project, are you guys planning on contributing any of the automatic optimization, the services to the community, to the open source project?
Yeah, we are working internally. We are planning. We have initiated the talks. It takes like a couple of phases to review and approvals. But the plan is the service that Steve talked about, the smart table optimization service. We are planning to contribute it back to the community, and it's very smart. Like we have saved a lot of money. We don't blindly go and optimize every data set. The smartness of this process is to find the right candidates, the right candidate tables to optimize in a right interval of time. So that gives us very cost effective, because if we start optimizing every table, then we'll be spending a lot of money simply on optimizing table, irrespective whether somebody is reading it or not. So yes, we do.
Great, yeah, looking forward to that. That's awesome. There was another question here. Yeah, how are conflicted data file when you're doing like compaction handled and like other writer processes coming in terms of like scheduling, and how do you guys do that? Conflict resolution.
Yeah, I think this actually we rely on the benefit of Iceberg because as many mentioned, they actually allow the concurrent modification of the tables, and they're separated by the snapshots. So compaction by itself does not change any content of the data files. They are just basically change the data size with some sorting. Unless the concurrent write has the impact on the schema to have the modification, most of compaction we saw does not interfere with the writes issued by users.
Cool. So the inbuilt stuff you find in production generally works pretty well.
Yeah, works pretty well for our use case.
It really works very well, because maybe I can share one of some of the tables, the large tables that we deal contains over 10 petabytes of data, one single table, right? That's one example. And we have like thousands of tables covering lots of data, different varieties. So we have like small tables, we have large tables with 1,000 columns. So we have different dimensions of tables. So fitting everything for all is not that easy. So one size does not fit for all. So we have to do all these customizations, make sure that it works very well for the rest of the ecosystem.
Nice. That makes sense. Yeah, definitely excited to see the work when you contributed. Did you have any preference on, I think more general, like normalized versus normalized as forms of Iceberg? I think they mean, normalized more of the schema design. How do you guys go about the normalized versus denormalized kind of table design and decisions there?
So that, I mean, table, that's a data modeling, right? So how that depends on how the tables are being queried by the consumers or reporting purpose, right? Most of the DE data engineering tables, they come onto the data lakes for the flat table concept, right? If the tables are with the various levels of hierarchical dimensions, then joins are expensive. So flat tables is what most people prefer as much as they can. But if they have proper use cases of I've seen that not in this particular use case, but in the past use case, if finance use case or marketing use case, they have different data sets coming from third-party data, then they would go by this different data modeling techniques. But that we support those data modeling techniques. We don't actually do the data modeling for our users. As a platform, we try to see what pain points they have. If any particular data modeling technique that they want to implement and it's not being supported, then we'll go and help them to support that.
Great, yeah, makes sense. There's another question here. Does the compaction apply to copy on write or merge on read tables or both? Any major or minor compaction policy differentiator considerations between them?
Yeah, I think right now most of our data users are still using the copy on write. I think for the merge on read, we're still exploring whether or not it's safe to release without. So I think the interesting part we figured out recently is that when we do the data compaction for the V2 table, which is merge on read, they're not actually covering all of the delete files because sometimes you're deleting a few records out of hundreds or thousands. So by default, I think compaction only look at the file size small enough that worth compactions. So I believe there's also in progress work in the open source community to handle this specific delta delete files so that we can actually properly remove them in future. So I think we're still exploring V2 for compaction.
Cool, great, thanks. It looks like we have time for maybe one more question here online. It says, yeah, I mean, I think you already addressed it, but anything else you want to add? Do your Iceberg tables contain deletes or updates? Compaction could fail, do a delete, winning the commit race and conflicts. Anything to add on that? But you guys kind of addressed it.
Yeah, so I think one thing to add is our compaction is by partitions. We don't just apply to all of the table all at once. So we, over the partition, say if it's partitioned by hourly, we see if there's any specific reason, like there's a lot of small file, we identify that first, and then we apply them. So that this kind of reduce our chance of collisions because we're more selective on what kind of partition are we optimizing for.
Yeah, makes a lot of sense. Okay, so that is all the time that we have. So thanks everybody for attending, both in person here eating lunch, as well as online. There was a lot of good feedback online that we could show you as well in the chats that people like the session. So thanks a lot, guys. Give it a hand for
Thank you.
Thank you, Jason.